So now recording is in progress. I told the people here that you see that there was someone asking for Zoom recordings, but I had problems putting them up directly the files. But here in video recordings, there is a PDF file with links to YouTube. These videos, they are given as videos on YouTube now that everyone can access, but I suppose that that isn't a big problem. I can remove them a while after the course, so you can. I'm not sure if you can download them, but if you want them, or maybe you shouldn't rely on video recordings too much. So today's stuff. What is it? How do I get rid of it? So is reciprocal space methods, as traditional type of methods to solve a structure. If we have traditional reciprocal space, then we also have direct space. And the traditional reciprocal space, that is to record the intensities, or the F squares, maybe we should call them, for each of the reflections. That is recording a diffraction pattern somehow, and trying to interpret that and find a direct space model. In principle, there's a problem to find what is called the structure factors, because they are not directly available. It's only the square of them. Or the square of the structure factor is, I can say that is structure factor times the complex conjugate of the structure factor, or maybe the amplitude square or something like that. So what we measure as an intensity of a reflection is only a number, a scalar number. But we would need, if we find this instead the value of the structure factor, the so-called complex quantity related to intensity, then it would just be quite easy mathematical calculation to find it. We have scattering length in neutrons. Well, maybe in X-rays also, versus we speak about form factor, atomic form factors. In neutron diffraction, the atomic form factor is just a number, usually at least a real number, and it's constant with the scattering angle. Otherwise, we have the traditional type of parameters, the structure displacement parameter. But we also have the phase problem. In order to be able to use these kind of data to find a direct space model, there are some problems to be overcome. I will just give a quick overview of the previous course. With neutrons, there is also a possibility to have an interaction with magnetic moment from neutrons. Maybe also from there is some magnetic photon scattering also, but that is very exotic and not. There are not so many examples. I hardly be done at the house, and you need to go to synchrotron installations. But on the other hand, magnetic neutron diffraction is quite standard, and it's can analyze magnetic diffractions. No. So perhaps one could illustrate this. We are after the real space density with X-ray scattering or nucleus density, or well, where are the atoms, either as in terms of electron cloud or of the nuclei. And if we have the structure factor, then it's quite straightforward. Solid lines or just mathematical operation. But unfortunately, we do have the intensity, and there are some problems estimating the structure factors. But we could, however, calculate something called the Patterson function, which is distance. And there are some problems to go to traditional real space structure from the Patterson function also, but well, perhaps we over. There are a lot of the electron density or the nuclear density, depending on what kind of probe, whether it's a proton or a neutron, it's essentially just a Fourier expansion, long infinite expansion. In times of space vector, instead of this power of pi I, one can cosine sine. But this is quite straightforward calculation. If you do know the coefficient with X-rays, we call them the structure factor, but we combine it some normalizing factor front with this one-dimensional structure to normalize it, the length of the unit cell. Perhaps one can infinity from plus infinity minus infinity or vice versa. Perhaps one can make it finite for the first. This is very in practice, and perhaps one can also half of the series is similar to the other one, and sum from 1 to n should have been. Then we also have an average. That's. But yeah, this is valid both electrons and electron density and nuclear density. The only thing that differs is the sort of Fisher form factor. So the problem here with a lot of measured intensities. Here we have structure factors. These cannot be measured because the amplitude measured. So here I have a structure with that are only positive numbers or negative numbers, some of them, and taking 25 terms in this series. You see that in the beginning the coefficients are quite large. Well, this one is large, and this one is large, and then they tend to be smaller and smaller, and the terms sort of converge to some kind of function. And this is a one-dimensional big calcium atom located at 3 different positions in the unit cell, right by this set of Fourier. And if we cut the series summation, various places, say that we have only 0 or 1 or 2 terms, then it doesn't look more than just some kind of average density. But already with 10 coefficients, the red curve here is kind of a good approximation to this sort of true structure. And with 20 or 15 or 20, it become better. So the only problem reconstructing this structure is to find whether this very case positive or negative. The requirement that we only have positive and negative pressure factor, that is showing that we have a centrosymmetric structure model. So if we invert it, we will get exactly back. If it's not centrosymmetric, then unfortunately the structure factors will be complex, all of them in general. But still, we can't detect the minus sign. There has been some kind of theoretical ideas about the measurement of the structure factor square, but also structure factor or with numbers. But in practice, we don't use it. There was some discussion in the 80s about actually trying to measure structure factors with multiple fractions. But that was never a hit. Too complicated to measure. It's much better to use simple method to measure and then methods for solving structures. The importance of amplitudes or this telegraphic basis of the structure factor be illustrated by these. This is a general non-centrosymmetric structure. There are 5 atoms in the model. We know the basis and we know the amplitude. And then I think that this is random basis and perfectly known amplitude. And the construction is, well, more or less nonsense. Not at all simple. The basis of the structure factor, otherwise the summation becomes some stuff. If that is known amplitudes and random phase, no, this is random amplitudes and known phases. That's at least what I said. Of course, this is random phases and perfectly known amplitude. Still, it's just need to know, but only knowing the structure factor first, then we can't go directly to this equation. This is obvious when you see this. Everyone knew that in the 90s and 300, until there were a couple of people, 50, I think, that actually didn't care about what was written and took random phases and put in the random phases the amplitudes, and not crap, of course, but some of the crap was negative electron density possible. So when they flattened or reverse the sign. And then one can calculate the diffraction pattern and use the known net to reconstruct it, and you still get crap. But use this, let the computer do it, because they don't have to work. And after 200 times, so something like that, suddenly the true structure appear. That works some of the time. This is known nowadays as chart. Flipping. There is some program called Superflip that is available as part of Jana, I think, or Jana. I don't say that it's the wonder method to solve all structure. It doesn't work. But don't let direct methods and Pettersson methods play. But they are the classical. This is one. It works also higher dimension 4 and 5 experiment possible, which perhaps there is a problem to apply that method. Higher dimension. With the center symmetric structure, then if this is the correct model, the only thing that you need to guess is the plus or minus sign. So we know the phases plus or minus, and then just random amplitudes. We could actually reconstruct something that is recognized when you know the answer. The phases seems to be more important than the amplitude. But how should we be able to know don't measure the amplitude? With random phases and very well measured diffraction amplitude, the result is like that. This is not possible to interpret. So typical three-dimensional structures is just the same as two-dimensional, but with yet another summation and yet another index and another coordinate. and some kind of length per area. We have normalizing constant volume. And also, instead of this summation, because the intensities in the diffraction pattern, they are discrete, only appear at certain point. But if you have a continuous distribution, you can also instead of a summation, fit point as an integer over continuous function. But then now let's see. This is the function, and then you need to know this Fourier function corresponding to the structure factor Fourier space a set of continuous Q values HKL corresponding to HKL. Good thing with the crystal is that at non-integer HKL, the intensity don't need some. You only need to measure the intensity there, the reflection. But sometimes you may not have with or scattering can occur, for example, in a point. This is a coordinate system with the origin, and you have a point here, and you have, if you have some beam coming in, we draw it like a beam scattered in the origin, or a beam scattered, the same beam scattered in the point P. So there is a length difference that give rise to the phase. This model gives some interesting. There are some interesting conclusions. Scattering phenomenon. We write two different rays, but I would like to say that it's the same ray. It's one wave, because it must be a single particle phenomenon. Otherwise, there should be a different diffraction pattern compared to how intense it can be. If it comes a lot of photons or neutrons, then there would be a time difference between the, and it's not. If you have a weak beam or a strong beam, you should actually the same diffraction pattern. So it's obviously a plane wave that is more than that. But still, there is a phase difference here, and this phase difference give rise to appearance. You can perhaps say that now the phase difference is the incoming wave minus the outgoing, or minus plus or minus, depends on whether we have a phase shift in the scattering phenomenon. But this length here, if there is photons, they travel with the speed of light, or neutrons with some limited finite speed. This phase difference, this length difference means a time difference, and thus, if we had the wave, the phase difference of the lower and the upper representative of. So we will have diffraction or interference. One can also say that the scattered amplitude is normalized to incoming amplitude times some kind of phase function, where R is the difference of the spot that scatters, and S is the difference coming and outgoing. For one point or many points, doesn't really matter. Scattering in one point is, and then just summing over a lot of different points, then we have a diffraction pattern. This amplitude that is in the outgoing wave, one can vary, and you get the intensity. If this is the amplitude of all different points, then the intensity is the amplitude square times all of the different points, and the difference in distance between each and every point, the Rj minus Rk. Then one realizes that the diffraction pattern is not necessarily dependent on the positions of the atom, but rather the difference in positions. All the possible interatomic distances, they make up the thing. And also, if there is an atom at J and another atom at K, this is some kind of value. But if we sum overall, then J will also be K, and K will also be J sometimes. So we have that vector, then is that somewhere else, completely the opposite vector. So the intensity is also a real number. That's kind of for me. Because this we can observe. Very complex equation of something. Yeah, the intensity that is it's related to the atomic distance. try to, we have the JK, and we make it opposite here, then this to a meter. Yeah, the sign terms, they will cancel, yes, because sinus something, sinus minus that is the opposite. They will sum up to 0, but the cosine terms, they will stay. So can type the density as a summation of only cosine terms. Now suddenly the I cosine, we should remove the I here. So this is the real quantity. This is also good because if you move the crystal in green, nothing happens. It will only stay in intensity. But if you would be able to a computer reconstructed structure factors, then you that they move around in complex ways or attain different values. So this intensity, we can factorize it perhaps that occurs from both the atoms. The atoms is perhaps a continuous density distribution. The neutron scattering experiment is just a point at the, but on the other hand, there is electron down that is magnetic. Perhaps there is density. Atoms or nuclei. This is a way to define a small part of the scattering from each atom, and then summing of different atoms make up the factor. Where we speak about the atomic form factor, which is this whole expression times some other. There is a no, we don't have a thermal parameter that is independent of the type of scattering. The thermal parameters, both for X-ray scattering and neutron scattering, they will tend to increase the intensity at higher scattering angle. And the graph is 90 over lambda, but well, it's essentially higher scattering to the right. We have, this is a copper atom, probably 29 electrons per angstrom, so 29 electrons per atom. So why? Otherwise, it should be 9. And if we have a very small thermal vibration, then the fall off is probably X-ray scattering. Not so fast, but with a high thermal parameter, they fall off very fast. So essentially, just after 0.5 in sin theta over lambda, we don't have it. So perhaps you need intensities out here, and then you need to cool the sample to thermal movement. These thermal parameters, they have different names. Powder diffraction usually B, but in single crystal it's U. They are the same except the factor 8 pi squared 100. But depending on what program you use, you will encounter it. And a typical meaning of the BW, it's only one parameter, then the atoms are only ball, which is rather okay. But if you have anisotropic, these ellipsoidal parameters or ellipsoidal description of the atoms, then they will be deformed balls. And the ellipsoids are sometimes described by the classic vortex, where one cut out 1/8 of probability. OTEP is the program, Oak Ridge Thermal Ellipsoid Plotting Program. From 19 billion at some point. Oh, solving structures. I wrote this when I got my drawing board. So what we did previously, 7 space, then heavy atom methods or direct methods or some other. Charge. And we have been testing this space determination for powder diffraction. The first trick is the powder diffraction. But when we know that, we can perhaps guess then finding clues. National perhaps find it. The phase problem, either we solve the phase, try to find the phase by called heavy atom methods, and one of the heavy atom methods named after a guy by the name Acheson, that is 1935, I think, published. Essentially, they go for if this green arrow is the true structural factor for each of the reflections, then if we can find a heavy atom, maybe only one heavy atom that is dominant, then we can, there are some methods to calculate that the calculate the Patterson map, or we can guess a heavy atom. Then we can see that, or we can claim that the red arrow is approximately the same as the green arrow, except that the heavy atom contribution and the different light atoms, they make up the true pressure factor. But perhaps we only know the heavy atom and we don't know these positions. Then we can still claim that at least the phase and the angle, perhaps not a good approximation, but a small error. Can use the known amplitude and the estimated phases from the heavy atom position, and then we can claim that these phases from the red one and the length of the one, then we can construct a Hamilton density and perhaps discover most of the atoms. Finding this heavy atom position, then we need to calculate something called the Patterson function. Sometimes, in principle, possible 5-atom structure, the different Patterson P map like that. So, for example, that the interatomic vector show up as a P here, and that vector show up as a P there. That vector. So this is a map of interatomic vectors, and this is a map of position. This could be derived from diffraction data, and then perhaps one could find down and have a cup of coffee and then out the that is a way to find at least. You have a lot of heavy atoms, and the Patterson map is crowded. Then it's perhaps possible. But for example, a structure like this, large organic molecule with a bromine atom, with the X-ray scattering, this would be kind of good example of heavy atom interpretation. Finding the bromine atom may structure factors quite okay, enabling us to reconstruct the rest of the atomic position. And bromine is a heavy atom for X-ray. Atomic number 35, so 35 electrons, while carbon atom, right? But for neutrons, not necessarily. And for neutrons, why does this happen sometimes? It's mouse. For neutrons, you need to look up scattering length, because a uranium atom, for example, is approximately as heavy as nitrogen. But in X-ray scattering, it would be complete. Perhaps there aren't so many heavy atoms that there are. I would recommend always try to combine X-rays. If you're into a neutron solid structure, that's usually more easy from X-ray. Because, for example, we have different large different scattering efficiency for X-rays. And there are heavy atoms. You have a metal, for example, a metal organ. Solve the structure first from X-rays, and then you apply that structure when you have the neutron difference. At least as far as when the neutron crystals they are the same as you have lots of information. You could try to solve it directly. Then it's that could also be have a simple structure and see how easy I have metallic acid. Atoms. Easy to solve with X-rays. Perhaps it's easy because I got very nice diffraction data, but I also got very nice neutron data. Also very cool at 30 Kelvin actually. So yes. Isn't
okay,
it?
it's not nice.
No, it is. So we can try that difficult. Or when I say that, interpreting heavy atom like that, then you need depending on base group, one can normally the value of the atomic vector in terms of coordinates of that. Unfortunately, we don't get the application with y coordinates. But this is the first. Then we immediately know that x for the atom should be something like 0.0. Z should be something like 0.08, right? And we don't know why. The interpretation of a heavy atom that's depends on the space group. Space group then the well, 10:42. Should we have a 5 minutes leg stretch or something like that? And
Excuse me.
Yes.
Hello.
Yeah.
Actually, when you stand a little bit away from the laptop, we can barely hear you. If it's possible, just to be a little bit closer to the laptop so we can hear clearly.
I can try to be closer, yes.
Okay, thank you. Thank you so much.
After the break.
Yeah, sure.
Yeah, okay.
Thanks.
Or I can speak louder. So, can you hear me if I speak like this?
Yes, now
Yeah.
it's better.
Yeah. Well, the alternative to heavy atom methods is simple direct methods, which is in principle trying to find the phases, but from the set of amplitude data, not depending on a known part of the structure or anything. There are a lot of different rules, and this is several courses on its own. It's hardly taught anywhere nowadays, except in a few places. In Bari, in south of Italy, for example, they still do it, and perhaps in Göttingen, where the people developing methods are working. But otherwise, it's implemented in standard software, and to a large part it's black box. It's available in the literature, so you can read up on it. It's linear algebra, essentially. There are some rules that relate phases of different reflections, or at least probably statistically, not necessarily correctly, but very often correctly. One of the most famous is from the 50s. It's Tyres. This is the family name of crystallographer. The sign rule, we call it the sign rule for centrosymmetric structures, or the Cyrus rule for non-centrosymmetric structures, which says that the sign, the plus or minus of a reflection HKL, times the sign of another reflection times the sign of a third reflection be 1, with the condition that the sum of these three HKLs come up to 0, because then this triplet is something called the structure invariant, and we can speak about triplet relations. Cyrus rule is one possible formulation of a triplet relation. There are quartet relations, pentet, sextet, etc., to whole diffraction pattern. It's usually enough with triplets and quartets. The basis, why is it true? We can look at some, there are 4 different equivalent structures, different phases, plus and minus. 1, 0 is plus, that means that the maximum density is at 0 and 1 full unit cell and 2 full unit cells. And when the phase is negative, -1, in the O1 direction, that is the Y direction, or the K direction, maybe in reciprocal space. So there is no density in the origin, but halfway through. And minus stands for a phase equal to pi, and plus stands for a phase equal to 0, or possibly 2 pi. So if we take 1, 0 and 0, 1, then we also have, if we combine these two, we have a diagonal vector also. And the phases of these two, the diagonal vector should be, according to Cyrus rule, plus times minus. What do we need to multiply the diagonal with? Should it be positive or negative? Well, it must be negative, because otherwise the product won't be +1. So the wave in that direction has a phase of pi then, or a sign of -1. We can see it as, now let's see. Negative. Why isn't it here? Positive, positive, then it should be positive. This is simple. oh yeah, sorry. This is the unit cell. So the wave is either here or here, then it's shifted half along the diagonal. If this is the origin, then here is the density wave, and then it's like that. It's maybe easier here if we have positive and positive, then we need to have a positive, then that diagonal wave is, this is the origin, then it's one distance here along the diagonal direction, and we have a maximum density. Well, that was not perhaps easy. But you may believe the Cyrus rule anyway. This is true. Better and better, more and more probable, the stronger the reflections are. If we have weak reflections, then we don't have any phase relations to speak about. Then the probability that the phase relations should be correct goes down to maybe, well, 5–10%, and then we can actually guess them. But there are a few. 10% of all reflections are quite strong in every diffraction. You can solve the structure usually and find where the atoms are. Then we can refine, and that's other type of methods to be used for fitting the atom positions better, so the calculated pattern should fit the observed pattern as good as possible. We need this. More of a standard least square on the even if there are complicated equations for diffraction refinements, but it's more of a standard mathematical method. You don't need to be in this not knowing the crystallographic phases. Two different type of problems actually, but we need to pass the first one in order to be able to do the refinement. Well, except charge flipping confirms that perhaps we can be quite sloppy with the structural solution, but that is perhaps theoretically not very for a mathematician that is not clear how it works actually yet. Magnetism with neutrons, we have a magnetic form factor. This is more or less similar in shape as the X-ray form factor. Not exactly, but if the magnetism come from the magnetic interaction come from the electron cloud, at least. Electrons, they are also magnetic, and thus they interact with the magnetic moment of the neutron. And photons, they are not very magnetic, but only a little bit. In very intense beams, you can get magnetic interaction. It may be identical to the sort of normal nuclear unit cell, this magnetic unit cell. Probably it could be a factor of 2 or some relation, commensurate relation to the sort of subcell. There could be an overstructure with the magnetic, but very often it is the same as the nuclear. There are analytic approximations for how to calculate form factors for magnetism. You can find them, for example, at ILL, an institute in Grenoble in France, and at very many other places also. Google for magnetic form factor. Fine. Structure solution from a powder. I think I've shown this before. High resolution pattern to be able to find a unit cell. And if you want to use single crystal method, then you need intensities. Within individual intensities, you can use traditional methods, either direct methods in reciprocal space, or if you can't really resolve a lot of individual intensity, perhaps there is room for so-called direct methods in direct space, real space. Then it's necessary to know something about the structure, how the molecule looks like. I think Ken will speak about that tomorrow, and it's some kind of combination of molecule can model perhaps with a force field or something like that. Very fast calculations, so it's easy to do. With Pauli diffraction, you also have a possibility to obtain low inaccurate structure model. Perhaps you can optimize that with some better quantum mechanical solid state model and verify it back with the diffraction data. And there are several methods nowadays, but Pauli diffraction is usually less informative than single crystal, but still higher than a lot of stuff could be obtained. I think this is the last view graph. I thought of actually, we had a look last week about barium sulfate, I think, with EXPO. EXPO is a typical program for reciprocal space modeling. The good thing with the reciprocal space that you focus on the diffraction pattern is that you don't need any opinion about the molecule or the content of the unit cell. If you have that, then perhaps you should rather directly go to direct space methods and not bothering about all of these finding crystallographic phases, and because there is a lot of possibilities to go wrong with reciprocal space methods, also with direct space. But suppose we have a pattern. Now let's see, how do I get out of this? So I did put up on the box area, Pauli diffraction and exercises, exercise 6, EXPO. I will put up some more stuff and demonstrate some things during the afternoon. But we can have a look at this one first. This is a typical diffraction pattern, or typical, it's a diffraction pattern at least, from X-ray powder diffractometer, where the first line is to theta start, step, and ending. So we will have sort of 4,501 peaks or something like that, a long list. Here I give a file, experiment file for EXPO, and I would like to warn you about trusting EXPO files directly. So if you copy this one to your computer, I can assure you it won't work, because have a look, structure T32, that is probably because the code name is T32, init data. Here it says that the pattern should be available at users, Lyric, Dropbox, Kurser, Powder diffraction och så vidare. So vidare. And you won't have this directory. So perhaps one should try to, in order for this file to work for you, you need to put it in the same directory and then keep that. This is a special feature of EXPO. It saves the whole path. So, but it could be horrendously difficult to realize that this is the problem actually. Here is the composition. It's thallium 4, silver 12, sulfur 8 in a unit cell with ABC equals to that.
So file save. What do you think? Should we go directly to on Expo or have a look at it with the high score first? Maybe high score? Hopefully, high score can we open, insert, perhaps a diffraction pattern, diffraction course 2023, exercises there. It needs an XRDML standard, but see if we can find something. STOE, ASCII, scan, that. I don't know. It was on a STOE machine actually, but if you go to the high score or if you go to Expo, the different type of software will require different input format, both of the instruction file and both of the diffraction data. So I hope this works. We'll see if we see something that looks like a diffraction pattern or an error message maybe. Could not import file. Reason while reading. Reason error while reading. We can convert the file, so we skip the problems with there. So read type 3 my computer. How should we find the file? I have it also locally on my computer, so my computer on D and on courses, powder diffraction, XRD patterns, T, and that one it was, yes. And then we write it, how to write it. Then write, so, sorry about this. Vad har jag gjort? There it is. I should have done this before. Extal.xobs and extal.obs. And we call t32.xy. maybe I have it. Sorry for powder. X. Så long journey. Copy. Dataset exercises. And we could perhaps, for high score to read it, I think we need to retype the extension from XY to ASP. But then I hope high score will read it. Open. Exercises E6 ASC. Yeah. Sorry about struggle. Here is a typical diffraction pattern from a powder X-ray diffractometer. We go for background. Accept this background. There is a green line down here, and if you change this granularity, if you take it down to a very bending factor to a very small value, then you see that it will the background will move around like that. So perhaps we should do. This is perhaps reasonable. Granularity, I think that is, if we decrease that, what happens? Yeah, then we start to model the peaks also. But that is perhaps, we should have quite enough high value to not to introduce some part description of the peaks. So this is probably okay. Then we go for locating peaks. And as usual, this significance value, I don't know what value it should be. We try with the previous value. Search peaks. Now, that was too large, I would say, because we missed these quite well-defined peaks. So I would decrease the significance, maybe from 15 to 5, and redo the search. This is probably better. Accept this one.
A question. Say something. That from time.
I converted it to column format also,
Oh,
because the .dat file
yeah.
problems. Fit some profile, and these peak positions are very well. Yes. Yeah. In high score. Yeah. The T32.asc, then I open it. Yeah. Background, treatment background. Determine background like that. Then I did search peaks. And the problem with search peaks is that we don't know how many peaks. The significance ratio is a number that you need to adapt. Try with the number that is saved for the moment. And then if it's too few peaks, then decrease the number. And if it's too many peaks, increase the number. And then when I found this, I did a fit. Here is a problem actually with using high score, because you see that the peaks are modeled as double peaks from an alpha 1, alpha 2 peak profile. So the positions, this was measured on a STOI diffractometer with a incident monochromator, so it's alpha 1 only. In principle, that should be possible to edit, but one could perhaps save it as an XRDML and edit that file, and then reread that file. Starts to become a little bit clumsy. But well, for the moment, it's not very difficult to. We'll see if we. There is some kind of. Maybe we had badly adjusted machine, so there is some shoulder actually. But the fits are not far from optimal. At 45, this is maybe at 50 degrees. How many peaks do we have? Let's have a look. We have something like 40 peaks up to 43, and this is alpha 1, alpha 2, so 20 peaks maybe. If we go for if we go for an, where did it go now? So, if we go for analysis and crystallography, we can see if we can find a unit cell. Use the first peaks. Maybe we can go down to 20. that should be enough. And what method do you want? Treor, Ito, Dickwall, or Dickwall 04? I vote for the last one. And here it comes out a probable unit cell. 8.79, 8.16, 7, 90, 90, 90, 500 cubic angstrom. Not indexed 0. That's good. Figure merit is 77. So this is probably a correct cell, or at least a cell that describes the first 20 peaks. Perhaps one should repeat this and go with more peaks, but I think this is the same unit cell 8, 16. Do we have a diffraction pattern, by the way? Can we refine it? Orthorhombic crystal system. The 100 seems to be absent, or at least we don't see it. Now, perhaps we should skip this space group determination and go into EXPO instead. We have a reasonable unit cell with a high figure merit, and this is the variation of peak positions, calculated peak positions compared to observed. And you need to look at the scale here. It's something like less than plus minus 0.02. This is what I would say a diffraction pattern without any systematic errors. Not so large, at least, because there is not a tendency of sloping upwards or downwards. There is random variations, yes, but except that seems to be not easily seen a systematic tendency. So good hope. We leave high score for the moment. Yes. Sorry. Did you do peak fitting on at least 20 peaks? Yeah. We can see how it is done in EXPO. File, load and go. Barium sulfate, we shouldn't. Now let's see, here we can't find, we need to copy from box because I don't think EXPO will find box. Perhaps not on my computer. So I copy that one, and well, perhaps it's enough we did 32.dat because EXPO can easily read that. Where did we have this kush? This PC. Kush. T. There it comes. And then back to EXPO. It wants to No, we don't have this experiment file, so then perhaps we need to go to new, yes, because we haven't run this previously. And use profile count file name. Then it will, the .dat file is one of the known types to Expo. But it's not one of the known types to HiScore, unfortunately. And also the ASC file is not one of the known files to Expo, but to HiScore. And until one realizes that, there are plenty of problems. No, let's see, read this. It detected the range directly, and it set the instruction name as the name of the file. It's X-rays, wavelength. This is standard wavelength, I think K alpha 1. If you want to have K alpha 2, you need to click that one, but this is pure K alpha 1, so perhaps we should stay with that. We can try a cell determination within Expo by Treor. Cell content, what was it? It was thallium 4, silver 12, sulfur 8. And direct methods, yes. Let's save this file. Has been created. Do you want to edit? We can have a look at it. Sulfur 8. This is one of the old Uppsala habits, working with thallium compounds. It's Rolf Berger, you know him. He introduced me to this long time ago. Everything is forgotten and forgiven. Let's quit this one, and here comes the pattern. So what do Expo do? Next, maybe. Then it detects a lot of peaks. We can use one of the, this is the select area to zoom. Well, these peaks are probably quite okay. And this arrow up here moves the cursor. There are a few peaks that is not detected, but they could very well be either impurities, or we just leave them if they are very weak. I would say that this is so far quite okay. When we come high up in the pattern, it becomes a lot more crowded in peaks, so maybe this is 10 peaks or something like that, but Expo determines at least 2. If you need to, we were lucky now, but if you need to affect the behavior of Expo, the pattern is perhaps a reasonable thing. You can modify the background, and you can modify peak search conditions. Also the indexing, you can actually use DQual here also. But we can go for peak search, and then nothing happens. Peak search conditions, yes. Then a box come up, minimum 2 theta, that is perhaps reasonable. Can we, no, we can't go back. We go back to the beginning. And then we say zoom a little, zoom. That is zoom. So this is 1, 2, 3, 4, 5, 7, 8, 9. Oh, it's a bit too few, maybe. So perhaps until 48 degrees. That is a possible modification. If you have a very, very crowded pattern, then it's better to leave them out, the crowded part, and just use the well-resolved peaks. So say that after 48, now we think that it's too crowded, then go for pattern, peaks, peak search condition, and then decrease this to 48, the maximum to theta. And clicking OK, then all of the higher angle peaks are removed. Let's see, number of peaks it says down here 28, and those 28 peaks is okay, I would say. If you want to remove, say, weak peaks, I think one can remove with that, add peaks, left mouse, or delete peaks, right mouse. So if we select that one and we want to delete this one, right click, removes it. If we are suspicious about the reliability of the peaks. But now we should perhaps now we have peaks up to 48 degrees, and in this case we could have very well chosen more peaks, but I mean 27 peaks now with the weak one deleted should be enough for indexing. 20 or more, but not many more. It is actually, you have a diffraction pattern with a delta to theta as a function of 2 theta. It could very well be so that you have some systematic error function. If these are the peak positions, then in order to, if you use all of them, then you need an error window like that. But say that we only use these, then this is actually more or less a straight function, and with erroneous cell parameters, it would even find the cell parameters with very small error window. So the difference from a straight line is quite small. It's easier to, you can try with all lines first. If you fail, then decrease the number of lines to the, say that you have 100 lines from beginning. And you don't know the error function because you neglect to use the internal standard, because that is tricky. Takes half an hour extra. Then decrease the number of lines, and then the probability will succeed is much higher. Approximately as we did here. So clicking next. That's so. First, Expo makes a fit of the peak positions. And did do something. Here comes out a couple of unit cells. Plausible unit cell parameters. A, B, C. They're two slightly different. And slightly different volume. The only thing that is A and B and C, they differ. This one is smaller in general, yeah, smaller volume also. So the difference between them is the zero shift. Expo applies a zero shift at different values and then tries to index. If there is a zero shift error in the diffraction pattern, then it's much higher probability that one should find a correct unit cell. Here there are two different. They are exactly opposite each other, but I can't explain why. That is hardly any reason for that. but one of them is higher figuramerit, M20. The Wolf figuramerit is 60 and 20 down here. In Expo, there is also a couple of other figuremerits. The new figuremerit is also higher than the other one. And perhaps the most important is number of not indexed peaks is 0 in both cases. So I would say if these would be two different cells, now we see that it's the same cell, only the difference is only due to a zero shift, two different zero shifts. And what will, I suppose that choosing any one of these we would end up in the same unit cell afterwards, so in the refinement. But take the one with the highest M20 value, unless you have a reason to decide otherwise. Yes?
I thought like 6 enough.
Why don't I get? Aha. But we can redo it. Yeah, I load and go, and then just read it again, and hopefully it forgets what has been. So what upper limit did you use? Okay, then it's 28 peaks. Yeah, okay, and we go for index. Or index, yes, no. Sometimes this next button doesn't react. Then it could be good to go back out in the large window, click, and then go back to the next button. So we'll see what happens. Oh, I got 6. What was the difference? The first one we did remove a weak small peak. Otherwise, nothing. They are. No, let's see.
That probably corresponds to the final.
Could be, yes. So otherwise, we need to go for more than double B edge and double volume. Figuremerit goes down to half. The biggest is 58, yes, with one unindexed. Let's see. We trust one unindexed is one too many, but if we can sort of don't care about it, we keep it. We think it's this unit cell. Then also the atomic volume is 21 cubic angstrom. This is if we do believe that, well, where did we got the composition from? That was actually this step. Here we would have been testing different, say, we know from electron microprobe analysis that it's 1 thallium, 3 silver, and 2 sulfur. But then the atomic volume is 84 and much too big. So maybe we should try to come down to something like 20 cubic angstrom per atom. So multiply by 4 everything. So it's thallium 4, silver 12, sulfur 8. That makes 21 cubic angstrom. If we multiply another time 2, then we will be down at 10.5 cubic angstrom. And this is very small. Too small, I would say. for normal metal interatomics and the sulfur atoms, they are quite large. But see if we can find the space group. Clicking that one, or if we know the space group, PMMM, then we can actually look at the diffraction pattern. With PMMM, all of the theoretical peaks here are printed, and it's very difficult to see, gain some information. Every observed peak should, of course, be present in the list of theoretical peaks, but there must not also be a lot of theoretical peaks where we don't see anything in the observed pattern. It's far from obvious that these three are not, they are, I would vote for not present in the diffraction pattern, and neither these two over here. But we let EXPO try to find the space group. We'll see what it does. Maybe we need to click next. I did some divided the pattern into 3 intervals. Okay, click next. The fitting is quite efficient. Press next to continue. Yes. Here it comes a long list of probable space groups: PBCN, PBN21, PBNM, etc., etc. And the figure merits here, well, with assuming that big figure merit is better than low, it's probably the upper one, but it's not very much higher than the other ones. We can see at statistics, it's only 0.85% of the structures in CSD that has this space group. Number of, I don't know the definition of these. This is centrosymmetric. So compared to this one that is non-centrosymmetric, I know that because I've been at these space group before. You need to look them up in tables. This is number 60, and I don't remember the number of this one, but somewhere below. So I suggest we choose PBCN and see if something happens. It will create a new data input file. Yes, okay. Then you see that some of the peak positions here were removed. This is probably a real peak, but no peaks here. Here are 2 peaks. Yes, I agree. 1 peak, 1 peak, 1, 2, 1, 2. There is a small one here. 1, 2. This second one is perhaps not obvious, but it's only the first one. And where we don't have, where we have a empty region in theoretical peak positions, we also have an empty region in observed pattern. So this is good, I think. Click next. What does? Okay, click next. Then EXPO will try to click next. EXPO will try to use the space group and try to extract as accurate peak intensities as possible. Here it suggests it does some kind of estimate of thermal factor. This is a Wilson plot, this normalization that we spoke about in the last course. EXPO suggests that there are something it's called pseudo translation effects. Should we use this information in extra? Well, we don't really know what it is, but why not? We try it out. It's quite quick to restart if we go into some chaotic behavior. Clicking next a couple of times and then yeah, wow. The extraction, here is a list of what it did. The extraction and the normalization of the data computed 2.2 as average B. Next one 2.2 and the third one 2.2 using this pseudo translation. And obviously it didn't do a large difference. This is good, I would say, with 1, 2 as an average B parameter is quite okay. And here is the structure. Now, the yellow is probably what's it called, sulfur, but which one is that? Maybe this is the thallium, this is the silver. Are there any labels? Yeah, that it's silverish, yes. So did we solve it directly? Is this a reasonable structure? I think it is, because no atoms are very close to each other, and the thallium atom are, if you remove the thallium, then they are in a tunnel. This is one of several possible tunnel structures. Where thallium is similar to alkali metal. It's thallium 1+. So it interacts quite weakly, but with the sulfur, thallium sulfide is stable compound, but not with the silver. If this is the correct structure or not, we can try to make this Rietveld, simple Rietveld in Expo, and let's go for automatic. It was up here, refine. No, how do I get back? Quit. Expo there. Here in we had it like that, and then there are two windows generally in Expo. One the viewer and then the main window. And in the main window there is a refine with a Rietveld. And unless we know what to do, we do automatic everything. And on this small box down here, we see that the profile R value is 4%. So that should correspond to quite flat residual line, and I would say that this is a flat residual line. There is some problems with fitting the big peaks here. Definitely some bad fit, but otherwise I would say that this is probably the structure. So quit this one and have a look at it. Yeah. A bit black box, and one could be happy, lucky when everything goes by automatic. Otherwise, there is a lot of possibilities in the refine. We could do a Fourier map if suppose we would miss an atom. We can select some atom. Which one? We select the silver atom here and modify, delete that one. So is this our structure? Yeah, why not? It's not easily seen. Let's see if it fits with the refinement. Rietveld. Hopefully it won't fit. Yeah, now there is some deviation. Quite large. And the overall fit is still quite good, 16% profile R value. Don't go too good. Yeah, there are definitely peaks that are too low and make up a large residual peak. And here also, here is a strange feature in the residual or in the RWP. You see, it seems to oscillate. It's not a steady, constant decrease. So we are not ready here, I would say. Then let's go for Fourier. How many info? 3 atoms in current model, yes. Should we do it observed? No, we shouldn't, because then we will get these 3 also. FOPS minus FCalc, 2 FOPS minus FCalc, that is the same as, approximately the same as FOPS. Or why not our traditional difference Fourier that we do in single crystal? This contour map, I don't know how it looks like. We can have a, let's try first, execute that one. And then we have a lot of peaks here. One of them is bigger than the others, and it's 1.7 from silver 2. And this one is quite close to, very close, too close, I would say. This is perhaps okay in distance, but it's much lower, so I suggest this one. Click that one only. And then we need to go to viewer. Then this is the Q1. What is the distance? And we select it. Select atoms or bonds. Q1, yes. And then we go to modify. What do you think that should be? What type of atoms? Change species to sulfur, silver, or thallium. I will guess silver. Hobson. Where are the sulfur? One. Modify. Change species to silver. I don't know what I did. So let's see if this improves the fit in the simple Rietveld. Perhaps not yet. It improves, but now we see here what it does for this. Expo does a lot of cycles in refinement, but only refines a few parameters in each cycle. It's considerably better than before, but far from could try most. That was perhaps a good way to make it more stable, and now it came down to the previous, or maybe this would have happened anyway. Running 2 times is perhaps necessary. So we destroyed our structure and reconstructed it via the Fourier, finding a new extra atom. There is also a lot of procedures in the below the solve menu here. We can explore and check. I think Expo can compute 20 different trials, trial structure from the direct methods output, and test each one of them, and also use them for the as extra information in the extra extraction procedure. Because with the structure, one can calculate a pattern, and then perhaps you have some idea about if there is a peak composed of two equivalent or non-equivalent, quite closely lying peaks. One of them is strong and the other one weak. Otherwise, extra will equipartition the peaks, I think, unless it has some extra information. Is it lunch now, by the way? Okay, then I think afternoon we gather in the 513, the other room, and then I continue to show some tricks and what's it called? Tips and tricks and species for Expo. Can we solve a organic structure, perhaps?